Hello. If you can hear me, please send some reactions in the chat. Well, I also solved only till G, at least till the moment I left. Okay, it's past the time. Should start. Maybe we can do it rather quickly. So problem A, we were given n and needed to find the biggest integer p, or rather we need to choose integers p and q such that their sum is n and p is at most q, and among those pairs we want the one with maximum possible p. Well, it should be pretty obvious that 2 times p is at most p plus q, because 2 times p is p plus p and p is at most q, so it's 2 times p is at most p plus q, which is n, so p must be at most n over 2. And since it must be integer, it means that it must be at most n over 2 rounded down, and n over 2 rounded down is actually a valid answer, because we can take q equal to n minus n over 2 rounded down, which will be n over 2 rounded up, and all the conditions are satisfied, so you just need to print n over 2 rounded down. For Proform, I will ask if there are any questions about problem A. I would hope not. Problem B, we needed to check if it is possible to construct a binary string with exactly n zeros, m ones, and we're also given number k, and there shouldn't be a substring of length k that consists of equal characters. So if n and m are equal, then obviously we can just alternate them, and that would be pretty good. I wouldn't say it always would work, because k could be 1, and if k is 1, then obviously this is impossible, because substring of length 1 always consists of equal characters. So if k is 1, then it is impossible. Otherwise, alternating characters would work. But if n and m are not equal, then like the characters that we have more of, we kind of have to have some groups of. And let's say that is this a correct abbreviation without restricting things? What does T stand for? Let's say that n is at least m. Then we have our m1s, and between them we want to place some zeros. But we also can place zeros before the first one and after the last one. And we cannot have k or more zeros in one group, so size of each group is at most k minus 1. And we can have at most m plus 1 groups, so the number of ones should be at most k minus 1 times m plus 1. And it turns out that if this condition is true, then it's always possible we can start with this, then fill 1 0 between each pair of consecutive ones so that we do not have long groups of consecutive ones, and then fill in the rest of the zeros into those groups such that the size of each group does not go over k minus 1. So we just need to check that this condition is true. If it is, then the answer is yes, otherwise the answer is no. That's it for problem B. Any questions about problem B? Someone in chat says disgusting tutoring style. I'm assuming it's tutoring. I don't know why it's disgusting, but you are free to close the tab and not watch it if you don't like it. Problem C. Problem C was about triangles, right? We were given some numbers and we wanted to remove the smallest possible number of them, such that all the remaining numbers, if we take three of them, they will form a non-degenerate triangle. So the condition, if we take numbers a, b, c that are sorted in this order, they form sides of non-degenerate triangle if and only if a plus b is strictly greater than c. You should know that from school geometry. Which means that if we how do we check if a set of numbers is good? We want to try and find three numbers such that this condition is not satisfied, but then it should be clear that to take three numbers that this condition is not satisfied, we want this number to be as big as possible and those two numbers to be as small as possible. So we take two smallest numbers and the largest number and check if this condition is satisfied. Then we can sort the array of numbers that are given to us. And then basically we are interested in two smallest numbers and the biggest number of the chosen ones. Since we have sorted array, let's say that this one is the biggest, this one is smallest, and this one is second smallest. Then the picture like this is doesn't really make sense because we didn't take any of those numbers, but then we can instead of taking this smallest number, we can take the closest one to the left of the second smallest number. So instead of taking this one, let's take this. it will make our life easier, and we have taken the same amount of numbers. Then we keep those two, and also everything in the middle we should also take, because that doesn't matter for us and we want to keep as much numbers as possible. So from this we can see that well, at least there exists an optimal answer that is a segment in the sorted order. So the optimal answer is a segment in a sorted order. And once we know that, it should be also pretty clear that if we fix the leftmost border of that segment, then our minimum and second minimum will be like those two first numbers, and we just want to take all the numbers that are strictly less than their sum, which would mean that we can try to find this point with a binary search, which will result in n log n complexity. We already spent n log n time to sort the array, but we can also do this part in linear time with two pointers, because when we move the left border to the right, the sum of two minimum numbers will only increase, so the right border will also move to the right and we can do two pointers. In any case, we need n log n to sort, and that's how you can check all the interesting options and choose the best one of them. Any questions about problem C? While you're thinking about possible questions, there is another comment in chat. Do GMs ever forget algorithms after taking a long break? It always seems like they know and remember everything. I don't know. Probably we forget something. But also, not a lot of people take long breaks and then go back to competitive programming. Why would you take a long break? All right, no new questions. Let's move on to problem D. In problem D, we had an array, and we could do unlimited number of operations. In each operation, we choose two indices L and R, such that L is strictly to the left of R, and then for all positions between them, we update AI to maximum of AI and minimum of AL and AR. We can do such operations as many times as we want, and we want to maximize the sum of all the numbers in the end. So since we are not limited in the number of operations, and all the operations can only increase the numbers, and like increasing the numbers kind of makes the operations stronger, so it kind of makes sense that we just do all the operations in like infinite cycle until the array stops changing, and then we just want to print the sum of numbers that we get in the end. How do I understand which numbers we will get in the end? Well, we can take a look at some position and try to understand how will it change. So we have some number here, then we will do some operations. To change that number in the operation, we need to take some number on the left and some number on the right, and then we will update this with minimum of those two numbers. Those two numbers themselves could have changed during the processing of operations, so it is not super clear what is the maximum possible value we can achieve, but we can kind of see that like we need to take something on the left and something on the right, and like if we try to update this number, we will need to take something on the left and something on the right, and this number is still like further on the right. So like you can get the get a hunch. I know that like you kind of need a number on the left and a number on the right to do anything. And yeah, it turns out that it is true that like the final value on position I will be maximum of the initial value and then minimum of what we can get on the left and on the right. So it's maximum over j smaller than iaj and maximum over j bigger than iaj. So we're taking the biggest value we can get on the left, the biggest value we can get on the right, then we take minimum of them and update each value with that. How can we prove it? Well, during the contest, I kind of just saw it, and so that was good enough. But yeah, we can prove the following statement by induction. Let's say that b1, b2, and so on, bn is an array at any moment, and I want to prove that bk is not greater than maximum of ai for all the numbers on the left, including ours. So I want to prove this by induction on k, then we will prove we can prove the same thing but for the right side, so it is also at most maximum on the suffix, and then we can see that like minimum of those two values is exactly this, and it is achievable by, well, clearly we just take the position that maximum achieves here, do the operation, and then AI will be the values that we want. Now, how do we prove this? So for k equal to 1, it is obvious because no operation can change the first value, because we to change something we need to choose L and R, and L should be to the left, but there is nothing to the left of the first value. And then if we have proven this for all like smaller values of k, then for given k, like it is true before some operation, and in that operation we will choose some L and R. If L is at least k, then this value doesn't change. If L is smaller than k, then the current value we are taking here is at most maximum over I at most L AI, and then we take minimum with something on the right, so it is even smaller than that, and then we update with this, so it is still not greater than this maximum on prefix inclusive. So we have proven this for all positions, then prove the same for the suffix, then minimum of them is exactly this, and it is achievable, so we just need to sum up those things. And to do that, we will precalculate maximums on all prefixes and suffixes with linear precalculation. That's it for problem D. Any questions? Build a Cartesian tree for this one. Yeah, you didn't need to. And I don't know how it helped you. Like, what we even trying to calculate with Cartesian trees? Minimums and maximums on graphics and suffix? We don't need Cartesian tree for that. Alright, if there are no questions about problem D, then problem E. So in problem E, we were given some segments. We wanted to choose lexigraphically minimum permutation that is good. And the permutation is called good if P is good, if and only if it is possible to choose an array AI such that for every position AI lies on the segment, and API is at most API plus 1. What it actually means that, like, if we consider indices in the order of the permutation, our array is non-decreasing, which basically means that if we basically we are choosing the order of segments. So this permutation kind of permutes the segments that we are given, and then on each of those segments we need to choose one value such that we will get non-decreasing array. So let's try to understand what condition should we have on the segments so it is possible to choose a value on each of them such that the range is non-decreasing. So let's say I will put segments left to right, and each segment will be vertical, and it corresponds to like choosing the value on this vertical axis. So let's say something like this. If we only look at the first four, then yeah, we can see that we can choose some points that in increasing order. But with the fifth one, like you can try, but it seems impossible. And the issue here is that there is this second position, and this whole segment is higher than the segment for the fifth position. But if the array is non-decreasing, it means that for every two positions I and j where I is smaller than j, so if we have I and j and I is smaller than j, then the corresponding numbers must be like AI must be at most AJ, but if Li is strictly greater than AJ, that is bad. So if you can choose, so if there exists I and j such that Li is greater than Rj, it is impossible. Um, so that's a clearly necessary condition. And it turns out that it is sufficient. Like if we do not have bad pairs of indices, then it is actually always possible to choose correct AI, and like you can just do it greedily, go left to right, and always try to choose the smallest possible value, which actually will be like AI will be maximum of LJ over J to the left inclusive. Why is that? Well, how do you choose AI greedily? It means that it must be on the segment, so AI must be at least Li, but it also must be at least AI minus 1, and AI minus 1 we have chosen as maximum on the prefix. Not inclusive, so AI will be maximum of those two values, which is just maximum on the prefix inclusive. And we can show that it is true that AI always lies on the segment. Obviously, it is at least Li because we specifically requested that, but also it is true that this happens because otherwise it would mean that maximum of Lj was strictly greater than Ri, and if we look at the position of the maximum, it will break this condition. So now we have a condition that is necessary, but also it turns out that it is sufficient, so it is a criteria. So we want to reorder the segments such that this holds true, and we want our permutation to be lexicographically minimal. When we want to build lexicographically minimal answer, it means that it must be done greedily. Like we need to minimize the first element, then minimize the second element, the third, and so on. So how do we understand which segments we can put on the first position? If we understand that, then from those segments we need to choose the one with the smallest ID, because we want Lexmin permutation, and then we just like continue building the answer one by one. So looking at this condition, our first segment, it must satisfy this. The problem is we do not know the order of all the other segments yet, but it doesn't really matter. Like how this condition can be broken with just the first segment fixed. Well, on the suffix we can do anything, so I here must be equal to 1. It must be broken with our first segment that is placed. And then we need to check if there exists j such that this happens, but this j can be of any segment that is still not placed, which is, well, right now all of them. Later it will be like some set of segments that we haven't placed yet. And that means that to check this condition, we just need to look at the minimum value of R among the still available segments. And we can only place some segment if its L is not greater than the minimum value. So our algorithm will look something like this. We're going left to right. Find minimum R over not yet placed segments. Then we can place some segment. So let's call it, I don't know, B. Can place segment I if and only if Li is at most B. Choose the one with minimum I. Okay, so this is our greedy algorithm. Now we need to find a way to implement it. Like the trivial way to implement it would be quadratic, because we need like linear number of iterations and then calculate minimum, like this again linear, so it would be like 4 which is square. But it turns out that we can maintain some sets. Like for example, to do this we just need to maintain a set of segments that is not yet placed, sorted by the right border. When we choose some segment, we will remove it from the set of not yet chosen segments, which will allow us to do the second step in of lock. And then step number 3, again, well, the step where we choosing something is the step number 4. To do this, we want to maintain a set of all segments that we can place, sorted by index. And yeah, we can like it is not hard to see that like from this set we will only be removing some numbers, so the minimum can only go higher. So this number B will only increase with time. Then for the segments that we can place, it will also only increase, because like more segments become available when B increases. So we want to maintain this set sorted by index, and to do this, like we need to maintain another set of the segments that are not yet like not yet allowed, sorted by left border. And like before doing step number 4, we will like look in that set, and if the like take the segment that is not yet allowed with the smallest left border, and if it is now good, if B increased like over their L value, we can say that it is now allowed to use. We can remove it from the set sorted by L and insert into the set of available segments that is sorted by ID. And then we do it again, like until we run out of the new segments. So this looks like a lot, but amortized it will be again and again, because every segment can become available only once. So if you have like a set of all not yet placed segments sorted by R, from which we will remove segments when we place them, then we need a set of all segments that are not yet available to place, sorted by L, and the set of all segments that are available to place right now sorted by I. We can do this whole algorithm in n-log n time. And then get time limit because tests are invalid. So that's it for problem E. Any questions about problem E? I can see that there were some comments during my explanation, but I think I already answered all of them. Great. So, any other questions about problem E? Yeah, if you want to try to optimize constant, so we had like set by Ri, set by Li, and set by I. So this doesn't need to be set, it can be just like a sorted list. Because we do not actually like extract from we do not insert anything, we do not take out from the middle, we just take the smallest element and it's like static, so you can sort it once and then just maintain a pointer to the first and removed element, and those sets can be replaced by priority queue, which is faster. But it will require a bit of work because for this set we do want to remove from the middle when we use some segment, we need to remove its R from the set of not unused R's yet. But when we are using it, we're only looking at the first element. So instead of removing it right away, we can just mark it as used in some array bit set, whatever. And when we are extracting minimum, just look at the element. If it is marked as used, remove it and do that while the top element is used. It still will be nlog n and should be quite a lot faster. But yeah, you definitely shouldn't need any of that. There is a comment interesting, at least for me. For you, it might be just common sense. I don't understand if there is a question there. Okay, let's move on to problem F. Problem F, we were given a tree. Then we define function f of k as follows. We look at some way of choose some k edges to mark. Then we build another graph. So let's say that this set of chosen edges is S. So the size of S is equal to K. Then we, for this chosen set of edges, we build another graph in the following way. So the set of vertices is just the set of vertices of the tree. So the graph is on the same set of vertices. And there is an edge uv if and only if let's say that this tree was called T, there is at least one marked edge on a simple path between U and V in the given tree. Then we in this graph we find maximum matching, and it was called with some letters that I do not remember. Let's say new. So nu of S is size of maximum matching. In this graph, and then f of k is maximum of this over all sets with size k, and we needed to find f of k for every k from 1 to n minus 1. Okay, so this seems like a lot of stuff, kind of scary, but it is not that hard actually if you understand, if you try to understand what this all means. So first let's try to understand like how our graph G will look for the given set of marked edges. So let's say that we have marked some edges. There can be several marked edges coming to the same vertex. And so our tree will look something like, so there is an endpoint of this edge, something here, and this vertex can have some other neighbors, so it still has its own subtree. Basically what I'm drawing here is like if you cut those edges from the tree, we will get some connected components. The number of those connected components will be exactly k plus 1, because for every cut edge we will split one of the components in two. Then an edge between two vertices in G exists if and only if those two vertices were in different components. Like if they're in the same component, then there is a path between them on which there are no cut edges, so there is no edge in G. But if they are in different components, then the path between them looked something like this, and it must have crossed at least one cut edge. That's like the definition of when they are in different components now. So basically our graph will be a complete graph with some clicks cut out of it. So like all the vertices are split into those groups by the component of the tree in which they appear after cutting all the edges, and then we draw all the edges between different components, but no edges inside of the component. Then what is the max matching? Well, by definition, it just means that we are taking pairs of vertices that are connected by an edge in G, and those pairs should not intersect. So that's the definition of matching. And we want it to be of maximum size. So what this means actually, this nu of S is max number of pairs of vertices from different components. And those pairs should not use the same vertex more than once. Now, this is a well-known problem. If you just have like some groups of I don't know, marbles, and you need to make as many pairs of marbles from different groups such that you do not reuse those marbles, that maximum number is like calculating that maximum number is a very well-known problem, and the answer to it is like if the sizes of groups are given by those numbers, then maximum number of pairs is minimum of well, just the total number of elements divided by 2 rounded down, because we cannot make more pairs than this, just in general, and the sum of all values minus the maximum of them. Why does this bound exist? Well, because in every pair we have to use one marble that is not from the largest group. So this is the total number of marbles that are not in the largest group. Like we took all the groups and removed the largest one. And in every pair we have to use at least one of them. So this is a clear upper bound on the number of pairs we can make. And yeah, it turns out that the minimum of those upper bounds is achievable by some stupid greedy, just take 2 largest groups and pair 1 marble from each. This will achieve this bound. So now that we know that, like let's go back and look at what we want to find. So we want to calculate f of k for every k. F of k is now the following. We need to choose k edges, then we cut them, calculate the sizes of components we will get. There will be exactly k plus 1 components. And then we want to maximize this thing. I again draw behind my camera. Can I move it somehow? No. I can do it. Okay, so to recap, for every k we want to choose k edges, then cut those k edges, calculate the sizes, and we want to maximize this thing. So this is just n over 2. The total size of all the groups is just the number of vertices in the graph, so we cannot affect this. So, this is again just n. So what we actually want to do is we want to minimize the size of the maximum group, and like not even that exactly. We want to minimize the size of the maximum group if it is bigger than half of all the vertices. And to do this, well, you kind of need to know something about trees. You like it would be super helpful to know what a centroid of a tree is. So for every tree there exists at least one and at most two vertices, such that if we root the tree in this vertex, or rather, like if we just remove this vertex from the tree, the sizes of all the remaining components will be at most n over 2. And we can find such a vertex in linear time by we can choose any root, calculate sizes of the subtrees, and then so we start in root, and then we go to the sun if the size of that sun is at least n over 2. Then we like stop at some vertex, and what does it mean? So the size of this thing is at least n over 2, but if we look at the like further suns, all of those are strictly smaller than n over 2. That would mean that if we look at like everything that is left up, it will be at most n minus n over 2, which is n over 2 again. So this vertex is centroid. It is possible for tree to have two centroids if like they must be connected by an edge, and removing that edge will split into two trees of size n over 2. In all other cases, the centroid is unique. We can find that centroid. Now the size of every component like this is at most n over 2. And it means that if basically the only component that can be bigger than n over 2 is the component of the centroid. So the only thing we need to do is to minimize the size of a component of the centroid, and that is done by just cutting the edges that go from centroid to its suns. And we want to do it in order of decreasing the sizes of those components. So like first we want to cut the largest suns and the second largest and so on. So the whole solution for the problem is to just find centroid, then calculate the sizes of subtrees for all the suns, take them, sort them in the decreasing order, and then we will cut them one by one, which will decrease this maximum. Like we start with n, then it will decrease by the size of each component we cut off. All the components, like other than the one with centroid, are smaller than n over 2, so they cannot like if there's a maximum, then this thing is greater than n over 2, and the answer will be just n over 2. So we just need to maintain the size of the component of the centroid and print minimum of n over 2 and n minus the size of the component of the centroid. So only sorting is n log n, and I guess it can be done in linear time. So there is a linear solution, but yeah, with normal sorting it would be n log n, but everything else is linear. Any questions about problem F? Those 2k different variables. No. That's number of edges we mark, yeah. The solution F is only wrong due to the space plus /n at the end of a test case. Well, so my solution on F is correct, is what you're saying. I kinda knew that, yeah. I reread it 10 times, and I was pretty sure that there is nothing I can mess up here. Um, as long as k is at least the degree of the centroid, we can make n over 2 pairs. Yes, that is correct. But it might happen earlier. Like as soon as we cut at least n over 2 rounded up from the centroid, we are good. Or even rounded down, I guess. Yeah. So that's it for this contest. If there are any questions about any of the problems, you should ask them now. Otherwise, we will be finishing this. So the max of j will be n minus all the components that we have cut from the centroid. Well, that is not exactly true. Like if we have centroid and two big components and we cut both of them, then maximum will be the bigger of those components, but it will not affect this formula. Like we only care about the largest component if it is strictly greater than half of all elements, and that can only happen for the centroid. What if there are two centroids? It doesn't matter for the solution. You can just use any one of them. But also, like, just cutting this one edge will already create two groups of size n over 2, which is enough. Like, now we can pair them up into n over 2 pairs. But like, you do not need to do a special case for it. Just taking any one of them as a centroid will work for the solution. And yeah, for any case, the answer will be just n over 2. Alright, if there are no more questions, then thanks for watching and goodbye. Well, I expected something with some crazy data structures, but this seems doable. Yeah, it like the code is super simple. But you need to understand the statement, and like it is true about many of the hard problems. You do not need to know a lot of advanced stuff. You just need to understand what the problem asks, and then find a way to calculate it and then implement it. But for implementation, like most of the time, you do not need anything. But even if you do need some data structures, like you still first need to understand what you want to do. Like with data structures, you cannot get like the data structures help you to make it faster, not just do something. As always, I do not like to answer the questions like what would be the rating of this problem on KF. But okay, I guess I have some frame of reference now after the blitz. I know that the first problem was 1000 and the last was 2200. This is certainly easier than the last problem in Blitz. Uh, so maybe like 1900 or 2000, something like that. Yeah, no, I understand the like why you want to ask that. Uh, I just don't like those questions because I do not know what those numbers mean. Like, what is supposed to be like an ideal spherical in vacuum problem of rating 2000? Like, that doesn't mean anything for me. But now I guess I have some frame of reference for. Like I know what can be a problem of rating 1000, what can be a problem of rating 1200, 1400, and like up to 2200, because I have solved some of them in like this intense environment. This would certainly not be harder than like B in first division. Like no way this can be put on position C. It's way too easy. Alright, now I'm definitely stepping. Again, thanks for watching and goodbye.